It's a pleasure to speak here. So, as John said, I do a Kahler case, and probably I will emphasize a bit differently. So what is a Kahler manifold? So in this talk, I assume M is first is a complex manifold. Okay. So locally, it's covered by Euclidean space, by open set in Euclidean space. So let's say in the local coordinate, so local complex coordinate, okay. So a Kahler metric is given by so G, see, so it's given by Gij bar. Okay, so this time this is a positive Hermitian positive definite matrices. Okay, so it's a Hermitian positive matrix value function. So, but itself is not a Kahler yet. It's just a Hermitian manifold. So this is we discuss this kind of metrics in contrast to this real Riemannian metrics discussed talked by John last time, because we want to make use of complex structures. Okay, so a Kahler metric, and they satisfy some condition. So this is positive. So this condition is the following: K so for all ijk. Okay. So why I will expand it in a moment. Why this condition is crucial. So usually what we do is a Kahler form. Okay, so Kahler form, let's say omega. So sometimes I put the omega g. Okay, but for simplicity, sometimes drop this index here. Okay, so this is defined to be a sum. N is a complex dimension of Gij bar dzi. Wedge dz bar. And normally what we do is we put the square root -1 in front of that to make it as a real form. You can check. Okay, so this becomes a real form, real two form. Okay. And then this condition, this Kahlerian condition, is exactly the same as d omega is closed. It's closed. So in particular, implies if M is closed, okay, if M is closed, then the H2 of M R is not zero. It's not zero. Okay, it cannot be zero. So if you find some manifolds like Hopf manifold, which second cohomology vanishes, then it cannot support any Kahler metric. Not every complex manifold supports Kahler.
So J is bar, the index J bar.
Yes.
What does mean bar?
Bar means complex. And the complex conjugate.
Ah,
okay.
Okay.
That's right. So one index in the holomorphic direction, another one in the concave direction, right? So in general, two forms you have a purely holomorphic direction, purely anti-holomorphic direction. Okay. So now here's, I'm sure this everybody can cover this. So So it's closed. So what is this importance of this condition? Okay, actually, in the Riemannian geometry, for example, we try to solve Einstein equations. In the Riemannian case, it's very difficult. It's not completely done. I mean, it's far from being completely done. But if the Kahler case, we have basically essentially complete solution. So the reason for that is because of this condition. Okay, locally, since this two form is closed, locally no topology, so you can also write as the exact form, right? So what you do is you can locally I means in the complex coordinates, this Gij can be written as this. Phi for some real functions, for some phi functions. Okay, say for real phi. Okay, so why is that? Maybe I explain a little bit here, since it's supposed to be general talk. So because it's closed, so I write this. I just give you a simple reason. So this is d omega. Sorry, it's closed. So omega can be written as d alpha locally. Okay, locally, not globally. Okay, so alpha is real. That's from a calculus probably. So then you can write alpha as one form into a 1, 0 part and the 0, 1 part. So that means, this means you only have alpha I, dzi, only have a holomorphic direction, and this is conjugate directions. Of course, this is just conjugation of that because it's a real form. Okay. So then you look at this. Since this only involves one holomorphic direction, another anti-holomorphic directions, so that implies d bar of this. The anti-holomorphic derivative of this anti-holomorphic part is 0. It's 0. Okay, so that implies this. It's simply because omega is of this form. Okay, so then this alpha 0, you are using a version of this for complex case can be written as d bar of functions. So now you get that. You get that. Or maybe they function up to some constant. You need to do some normalizations. Okay. So locally you have this. So globally, if you have a two Kahler metric, omega prime. Say in the front law we write Kahler metric in terms of its Kahler form. Okay, if you have two Kahler metrics with omega same as omega prime. Okay, so that means that their cohomology class are the same. Okay, so they represent the same cohomology class. So then omega prime can be written as omega plus the square root of dd bar. Maybe I want the phi to be real function. Okay, so this dd bar phi. Okay, so this again is always normalization to make things. Okay, because the dd bar is not quite real yet. Okay, so this is by Hodge theorem. Okay, so locally as simple as that. Globally, you need to appeal to some deeper theory. Okay. So another thing you can say to make it a connection to a last talk is a Kählerian condition d omega 0. This condition assures that the connection defined, the Vicevita connection we defined last time, preserve a complex structure. The complex structure. So in this time, it simply means the square root of 1 is constant. with respect to this derivative. This derivative. Okay. So because you have three structures now. One is the Riemannian metric, the metric G here. One is a complex structure, and you want also symmetry. So these three conditions, why they can be made possible simultaneously, you need this. Okay, this is equivalent to that.
So, silly question. So this -1 means that how the rotation by the
square root. So I want to say this a little bit misleading. Say this is constant, but I want to say as in terms of coherent derivative.
In every tangent space
by changes, yes.
By this complex number.
Square root is the complex structure.
Yeah. So J. So I should say J is constant. Okay.
Okay, capital J.
Okay. If I don't write square root of 1, I write square. Yeah. Okay.
The field structure, what is it?
Mm-hmm. Okay, thanks. So now let me give you some examples. Okay. In the Kahler geometry, this simplest example, or say homogeneous example, this is complex projective space, which is defined to be a Cn plus 1 minus origin quotient by this. Any questions? No? No problem. So this things means Z1 is equivalent to this prime if and they are, say this is Z to simplicity, this is Z prime, this is up to a constant. It's constant. Okay. So say this is a complex projective space. So this space has a metric. So you can write this metric as follows. So this is say Z0 is not 1. So you look at the open set inside of this. So I make life simpler. So it's inside the CPN. And the Z0 is not 0. Because of this relation, so this can be equivalent to a Cn by maps to a Z, maps to a Z1 over Z0 to Zn over Z0. Okay. So let's say this is a W1 Wn. Okay. So that's a local complex coordinate. Then there's a metric so-called Fubini-Studi metric. Okay. So it's a Fubini-Studi metric. This is given by a derivative. Let me just write this way. Log 1 plus okay. So all in terms of this. So this is given by 1 plus Z square, W square, dW minus sorry. I'm not used to this. So this when you to see two indices, you do a summation. Okay. So this is this. Okay. And this is homogeneous. This is homogeneous. This square just means this term here. Okay. This is homogeneous. So usually, so for formulae, you can simply write as this. But this is not quite a function. So it's function only in the sense up to some gauges. Okay. So this is homogeneous, and this is the best Kahler metric. Okay. And secondly, say if M is a complex submanifold, sometime, okay, then omega Fs restrict to this M is a Kahler metric. Okay. So it's a Kahler metric only. Okay, it's a Kahler metric. And so this gives you, since for example you take any algebraic manifolds, say as zeros of some finite many polynomials, homogeneous polynomials, then you take the restriction, you get a Kahler metric. You get a Kahler metric. Okay.
Yeah, I don't understand.
Yes.
Metric G is still without Gij is tensor. Yeah.
Gij is tensor. Yes.
And you also have derivatives of coordinates.
Yes.
In the right hand side.
Yeah, right hand side. Yes.
Maybe you're not.
Oh, sorry. You're right. So this means this. So I guess I write this minus. Sorry. Okay. Thanks. Okay. Yeah, right. So somehow I expanded this side. Yeah. So this way you get the Kahler metric, and but on the other hand, you can get a lot of Kahler metrics for every sigma of in the SL n plus 1 C. Okay, so this certainly induce automorphisms of CPN. Right, just acting on coordinates here, acting on these homogeneous coordinates here. Okay, so let's denote these homogeneous coordinates by so this is given by Z Vn. This is a homogeneous coordinate. This bracket means all equivalence classes of this. Okay. So then what you can do, you can look at the star. You pull back, you act this on your Fubini-Study metric. Okay. Of course, on CPN it does not change anything. It's still intrinsic the same metric. But when you restrict to n, you might get different metric. Okay. So you get new metric. It's also Kahler metric. It's also Kahler metric. Okay. So this way, if you check, this way at least you get you look at the S. So I need will give you a check to quotient by UN plus 1, which is subgroup of this. Okay. And if you check, you can check if a sigma is in the unitary group, it does not change this. Because if you look at the Fubini-Study metric here, at least the formally, it's just got by square sum of that. And this, if sigma is unitary transform, it does not change this at all. Okay. So you will get the same metric. So this is all possible. Basically, this is all such a metrics. So you get a class giving any, at least giving any algebraic manifold. So this, I should say, this kind of manifold form a major class of Kahler manifolds. And used to be a conjecture says by Kodaira says any Kahler manifold can be approximated by manifold this type. It turns out it's not quite true, but but anyway, this still these provide large class of these. Okay. a lot of interesting examples. For example, Calabi-Yau spaces and so on all come from these things.
Should I think about this last conclusion that locally on a given variety, on a given manifold,
Yes.
all the complex structures, all the Kubler structures,
Yes.
are parameterized by
Not all. These are they only say this type.
only that.
You say type, but you might have a different embedding. For example, you use this segregate mapping to map this into bigger projected space. Then you do the same thing, you might get another family of that, which kind is bigger than that. Okay. So in fact, it's a so there is a so. But this is actually not too far from all the Kahler metrics. Okay, so let's recall one thing. So there's a Kodaira theorem. Okay, Kodaira theorem says the following. So I state in the way I fits into my discussion here. So M. And giving a m omega such that, say, Kahler, this is in the integer class. Okay. So it could be in the rational class, doesn't matter. Okay. So then M is such a manifold. Okay. Can be embedded into some projected space. So more precisely, how they did it. So it's not a proof. So let's see. This is it's not a proof. That's a real outline. Okay. So this says what? How do I get this? So you look at because this is integral class, you can see this omega is maybe up to 2 pi of a first-term class of some line bound. So here is some holomorphic line bound. Bounded on M. Okay. So since omega is positive, so what Kodaira did is for choose. So you look at the line boundary, you look at the tensor. So L is defined to be a L tensor itself, L times. Okay. So giving a line boundary, then you can find. So this is the extension of functions. Okay. So you look at the L to this. So this is all holomorphic sections. I guess I'm using a little bit of cohomology. This, okay, all the homologous section of L over F. Okay. So then this is so look at the holomorphic sections, and then you can use this to embed. Take any basis. So giving any basis of this group, so you can X to embed your M into some projected space. Okay. So Kodaira theorem, Kodaira proved as L sufficiently big, you can also choose this, and the basis satisfies this. This is embedding. It's embedding. Okay. So at least under this cohomological condition, this integral class condition, your manifold is of this type. And then
why L should be ample?
air should be ample because this is a Kahler metric. It's positive. Okay, good. So I think it's you know more algebraic. So ample is because algebraic. Where's my things? Rest. So maybe I spend, I think my time is, so maybe I just say a few remark. Okay, it's not a Riemannian metric, curvature. Sorry. So giving a metric, so this condition shows this condition says this omega is a curvature form of a Hermitian line bundle, a Hermitian metric, sorry, on air. Okay.
So C1 of L?
C1 of air, yes, right, thanks. C1 of air, okay. So it's a Hermitian metric on this, so let's say small h. Okay. So now this h together with the metric, you can define inner product, Hermitian inner product on air or on any air defined to be these things, and h is you have a Hermitian metric on air, then you rest it 10 air times, you get Hermitian metric on the air. Okay. Then you integrate against the volume form. So this is just a volume form for metric. So you get this Hermitian inner product. So then in the Kodaira theorem, if you choose the orthonormal basis, so if this basis is orthonormal basis, okay, instead of doing this, instead of this arbitrary basis, okay, since we have metric now, so then and you do embedding, then we know. So then what we can do is we can do this. Maybe I write this. Then we define say omega depends on omega and air, okay, and x a function to be a summation of norm. But this is a pointwise norm defined by h air. Okay, so maybe I put it this way. So h air s bar I from 0 to n, the basis. Okay. So even though you have a choice of this, so even if you have a choice of this base orthonormal basis, but this function actually you can check independent of the basis. So lambda only depends two things. One is this metric, one is air, where you use the embeddings. Okay. And you can check what the. So what one can prove is the following. So okay. So theorem. This I proved in my thesis, and later extended by others. run, and so on. Zerdish, Kathleen, and so on. Okay, so I only proved C4 convergence. So this one, omega L of x is actually some constant A0 of Ln plus the low order term. Okay, low order term. So you plot some function which of low order in L. Okay. So A0 can be computed easily because if you integrate along the manifold on both sides, since this is also normal basis, this is exactly dimension of H0. So this A0 can be computed in terms of Riemann-Roch. Okay. So this thing, so it's just looks like pointwise version of Riemann-Roch. But what does that have to do with what I said there? Okay, a Kahler metric, and so yes.
SE is orthogonal bias in what?
SA is also normal basis of this group. This group. Sorry, it's because this chalk is you have this air. I look at also normal basis of that. Okay, is that clear? Or it look puzzled. So so this is also normal basis of this group. Okay.
And metric H is
Now, with respect to this inner product.
no, and H is what is H in this definition?
H is commission metric here.
Should I think about this theorem about this equality on the very bottom? I don't know, as a kind of Riemann-Roch for
Yes.
context.
If you integrate that, that's exactly get Riemann-Roch. That's why. But the key point here to prove leading term is constant asymptotically. Okay.
And this A naught is dimension of H naught.
Yes. N is the dimension of manifold.
Yeah, but A naught.
A naught is not. A naught is constant.
Just constant.
Yeah, it's given by Riemann-Roch.
Okay.
Yeah. So then if you look at, in particular, that implies 1 over L log of rho omega L will convert to 0. Convert to 0. Okay. As L goes to infinity. I mean, it's much weaker than that. Okay. So now, if you compute over this, so what does that tell you? Now, first, this is nothing else but the Fubini-Studi metric, restrict to n, and maybe you divide by 1L and minus omega. Okay. Because here you have a Hermitian norm and you have a basis. If you take out the Hermitian norm, that's exactly your Fubini-Studi metric. Okay, you do it locally. Okay, so if 0, that implies this goes to 0. So the conclusion is, since this is going to be any arbitrary Kahler metric to start with, only with the cohomological condition, then the things I said there, this SL, so let's see. So I usually denote by KL. So let's pause it. It depends on embedding. So let's give a symbol here. Okay. So So this is air union. The closure is all Kahler matrix. With a Kahler class given by a 2 pi alpha. C1 here. So space of Kahler matrix, you can think is just kind of limit of homogeneous space, right? Because each of these homogeneous space. Right? So that's at least for in case of algebraic manifolds, I give you a kind of structure.
Oh, this depends on N.
Which?
Kappa N. Oh, it's dependent on
Kappa. Say it again. This is chi, yeah. Yeah. So air depends on embedding because for each of these I have this. So air depends on embedding. Okay.
So on the very top, on the very row,
Yes.
A goes to 0 or to infinity?
Air goes to infinity. Sorry, thanks. Okay, I add 1 over 0. So yeah, so air goes to infinity. Yes, sorry. So okay, so let's give you all the Kahler matrix, and actually give you exercise. Maybe you can check. This is actually, maybe you can imagine you try to prove more elementary. So let's say M is S2, which can be seen as a C 1 point, right? Just do a projector space. And then any omega basically can be written as E minus phi, some standard metric. So this part is just Willis loaded metric, and any other metric is of this form because it's 2 dimension. No other variations. Okay. So Hermitian metric is basically given by this. So Hermitian metric is given by E minus phi of square. Okay. And what is H0? So air here time is air is simply a first Chen class of this so-called hyperplane bundle. So let's see. Okay. So H0, maybe this is of air is just a C2. Okay, it's a C2. And H0 for M, air, okay, maybe I'll not use the air, is just all the polynomials of degree less equal to air plus air, I think less than air on a C. On all the polynomial or less equal to air on a C. Okay. No, it's because I want to identify with one open set. It's if homogeneous is exactly air. Yes, I inhomogeneize it. Yeah. I just try to make it simple. Otherwise, it's a homogeneous space. Yeah, you're right. If this is a homogeneous space. Okay. So then this is if you look at the base, you look at this condition to save time. I will not write down. So maybe you can check if what I said is true. The above is true. So this time it's just become a phi. I get a family of functions, log of some basis of polynomials, and maybe normalized by air, divided by air, and it goes to suppose goes to a phi. So the conclusion. So why I say this is just the above is true just means this, right? Because you interpret it's just like kind of vectorized theorem, but it's because this is polynomial. We discussed it in a different way. Okay. And this is also normal basis with respect to this inner product.
So, is it true that the
this variety of all Taylor metrics,
Yeah.
CP2,
Yeah.
is infinite dimensional complete projective space or something like this, or it's not?
Say it again.
So on the third row, there is a description of a kind of manifold which describes all Taylor metrics.
Yeah, each of these is 5-dimensional, but the closure is
but
infinite.
in this particular example, that this
This is as L goes to infinity. It's again, it's infinite dimensional in that. So actually, it's still an open question. So how uniform this convergence is, okay, even on S2. Okay, so maybe in the last 5-10 minutes, so let me just say a little bit. I mean, this problem, this was proved in the late 80s, and then improved the convergence was given by late 90s. But this thing still goes on actually to a recent progress, which I'm not going into that because it takes too much time. Okay. So in the Kahler geometry, one topic in the Kahler geometry, which is related to what I'm going to say last time, one topic is about the Kahler-Einstein matrix on a canonical Kahler matrix. Okay. So actually, this is probably most active research in the current Kahler geometry. So what you canonical here means the following. So giving a Kahler, so you ask, and maybe I forget the general case. So one is a definition. So it's a Kahler-Einstein metric, a Kahler metric. So metric omega is a Kahler metric. First is a Kahler metric. Which is Einstein satisfied. And the Ricci curvature of omega is lambda omega. Lambda is constant. It's constant. Okay. So where maybe I should say a bit about the curvature here. In the Kahler geometry, okay, the curvature, because of this complex structure things, because of this d omega equal to 0 condition, we actually curvature only has those components. Okay, and this is defined in terms of summation S, and so summation PQ d P Ij and d KL dzq. And the Ricci curvature, the Ricci curvature is just summation of this, K and L. Ricci curvature is maybe I put this way. It's a symmetric anyway. So Gij bar, Ricci. Okay. So it has a form. You can see this is nothing else but in the local coordinates, dzi, dzj bar, log minus determinant of gkl. this says the Ricci omega, which is defined to be a square root of this Ricci I j bar dzi dzj bar, and which is equal to, according to that formula, is just minus square root dd bar of log of determinant. Okay. So in particular, it's closed. It's closed. So my chain value theory, this represents the first chain class. Or maybe 2 pi of that. Okay, represent the first chain class. So this condition tells, so that implies the corollary is this if C1 if n admits a Kahler-Einstein metric, so if it's closed, let's say. So to simplicity, I only consider the closed case. Okay, and has a Kahler-Einstein metric. Then this first chain class is definite. So this is equivalent to say the determinant of holomorphic tangent bundle is either lective or trivial. So lective means its conjugate is ample, okay, or is ample. Ample. Yes? Ricci, I define this way. Ricci curvature is a tensor. So I define this. I set this form as this. You can define this is a global defined form. So it's of this form. So it's closed. No?
Usually, Ricci is symmetric tensor.
Ricci is a symmetric tensor, that's right, in the real coordinates. This is a complex coordinate, it's a Hermitian symmetric. So this is okay. Okay. So it's just like Kähler metric, it's a Hermitian symmetric. And the corresponding Riemannian is symmetric. So it cannot be made a form. Yeah.
What is the meaning? I don't understand.
So this definite means this is let's put it this way: the holomorphic tangent bundle of this. So this called anti-canonical bundle is ample. So let's forget about this. So definite means it can be represented by some form which has definite positive. Can be represented by some two form, which is a positive, negative, or 0. Okay. So if it's, for example, globally, yes, this is equivalent to say a canonical line bundle is ample. Okay, if whatever you know these algebraic things. Okay. Okay. So this is this. So maybe I stop it now. I just state and so it's known before. So if the theorem. So first case by is if C1 is 0, there is a Kahler-Einstein metric. So this time actually is lambda is 0. So it's a Ricci flat. Curvature is flat. So there's a Kahler metric with a Ricci curvature equal to 0. So now they call the Calabi-Yau metric. Okay. So there is also a Kahler-Einstein metric with lambda Lector. Okay. The positive case is more tricky. I don't want to. It's only recent progress. So I think I don't have time to talk about it. So next time I will talk about Kahler-Ricci, some simple thing about Kahler-Ricci flow, and may come back a little bit to this Kahler-Einstein metric.
Can you repeat, please, the case of the first Tian class?
Yeah, it's 0.
Less than 0 case. What did you say? Can you just repeat?
So if a C1M is 0, if a cohomology class is 0, there is a Kahler metric with Ricci 0. If less than 0, there is a Kahler-Einstein metric with lambda equal to -1 with negative Ricci curvature.
And you said something about why it is different when what did you say in corollary?
Corollary, this is a necessary condition. So this is say, and this turns out to be sufficient too for those two cases. That's a difference. Okay. So lambda is appeared here. So that says the Ricci curvature as a metric is constant. Okay. The positive case is more tricky. You need more conditions.